Okay, good morning. We'll start the After Café presentation. So my name is Jordan Meyet. I work at MCL in the Molecular Spectroscopy team. And today I will be discussing about Rigor Matters, accurate analysis at elevated temperature. So in material science and engineering, understanding the properties and structural change of material as a function of external stimulus, which can be electrical, chemical, or thermal, is crucial for the development of advanced technology. So in order to gain knowledge on material property under thermal condition, thermoanalytical instruments were developed. The most commonly used thermoanalytical instruments are the thermogravimetry analysis and the differential scanning calorimetry. So the TGA allows you to study the weight change as a function of temperature, and the DSC allows you to study the change of heat flow as a function of temperature. So here is a picture of the design of a TGA on the left and a DSC on the right, and we can see there is a lot of similitude between those two designs. First of all, both of them have a sample cup. They are both attached to a balance wand with a TGA with a balance wire, and for the DSC, a balance arm. And in both cases, the thermocouple is either very close to the sample or touching the sampling cup. So this is important because those thermoanalytical instruments have been optimized to do thermal analysis. So they have been designed with an optimal heat transfer. They are using small amount of sample in the few milligram range. The thermal conductivity of the sample cup is great. So usually we use aluminum or platinum pan. And the thermocouple is close to the sample. Despite those optimal design, the instruments still need to be calibrated. And I will just present for the TGA the way the instrument is calibrated. So to do the calibration, we need to use a high purity reference material. In the world of TGA, we use different either metal or alloy that have very well-defined Curie transition temperature. So Curie transition temperature is the temperature at which the material change its magnetic property. So we load the sample in the TGA, tear the instrument, and then put a magnet under the sample, which leads to a gain of mass of the sample. And then we do the temperature calibration, and at the Curie temperature, the weight goes back to its initial value, which gives you the actual temperature inside the instrument. So there is no change of sample mass, it's just the change of the property. What is important to know about calibration of those type of instruments is the calibration is highly sensitive to the purge gas you use, because different gas has different thermal conductivity. So the thermal conductivity of helium is different than the one from air, which is different from argon. It's dependent on flow rate, and it's dependent on heating rate. So while TGA or DSC are very important to understand the material, often it doesn't give a full picture of what's happening inside your material. And for this reason, many scientists wanted to develop thermal analysis coupled with spectroscopy or diffraction. So the advantage of non-ambient spectroscopy or diffraction is the possibility to identify the phase transition or the process of decomposition, the reorganization of the material, or the reaction mechanism. So on the bottom left, we can see an example of non-ambient Raman spectroscopy looking at the phase transition of sulfur as a function of temperature. And we can see at room temperature, we have the alpha phase that transforms to the beta phase at 90 Celsius and goes to liquid at 100 Celsius. In the middle, it's an example of non-ambient XRD experiment of thermite, and this allows to see the change of phase of the thermite as a function of temperature. On the bottom right is the example of the decomposition of calcium oxalate monohydrate as a function of temperature. And on the top is environmental TEM of platinum palladium particle on alumina, showing that under oxygen environment at elevated temperature, we have a vaporization of the metal. So all those information are possible in combination of thermal analysis, giving more insight into the material. While to do this type of experiment, we cannot modify the instrument to integrate the temperature stimulus. Companies have developed different type of accessory allowing to do that. So on the top right, we have an example that I will discuss later about the ARIC praying mantis temperature chamber that allows to go up to 600 Celsius. In the middle, we can see the Lincoln stage, which allows to do high temperature analysis with a microscope, so either FTIR or Raman. On the right, we see some accessory from AtomPar in order to do high temperature experiments using XRD. One of the main issues with all this accessory is that there is always a compromise between the design of an accessory and the accuracy of the temperature we can achieve, because all this accessory needs to accommodate the spectroscopic or diffraction technique. So one of the main thing that happen in the drift of temperature comes from the fact that the temperature probe is often away from the sample, because we cannot do the spectroscopy and have the temperature probe where we are doing the spectroscopy. The amount of sample we are using is larger, so often in the 10th of milligram up to 100th of milligram, which leads to difference of temperature at different place of your sample, and just the design of the heater in order to accommodate the spectroscopy or diffraction. So in order to correct that, there is a calibration strategy we can implement, and there is two different types of calibration. The first one is internal calibration, the second one is external calibration. What I mean about internal calibration is we record the temperature, we use a process to have the temperature while we are doing the analysis, which gives a more accurate measurement of the temperature and makes it independent to the sample condition, the sample or the condition we are using. So the first type of internal calibration we can do is using a thermocouple that is where we are doing the analysis. The problem is when we are using spectroscopy, we cannot do that. Otherwise, we cannot analyze our sample. The second possibility is using a standard with a thermal, like a known thermal response. So we just add the standard to our material. One of the main issues by doing that is we have an additional signal that we need to remove. And we have a possibility to have this standard reacting with our sample, and so we don't know if the behavior comes from the sample or from the interaction. The second and most widely used method to calibrate those accessories is an external calibration. So either using a thermocouple, which gives you an accurate measurement. So you put the thermocouple where you're doing the analysis, you cannot do it at the same time, and you create a calibration curve, and then you assume that for your material, you have the same temperature profile. One of the issues with that is it requires a good contact between the probe and the sample, and it's highly dependent on the condition. So if you change the flow rate, if you change the gas, then this calibration might not be valid, which is true for any external calibration. The second possibility, which is what is used for TGA, is using a thermometric standard. So when I'm talking about thermometric standard, I'm talking about a material that changes its property at specific temperature. So the property can be the melting point, crystal phase structure transition, magnetic structure, this is what we saw for the TGA, thermal expansion, or gas-solid chemical reaction. So the advantage of the thermometric standard is it is accurate, but depends on the condition. So today I will be talking exclusively about external calibration for two particular accessories, one for FTIR, one for XRD. And I will use thermometric standard with specific melting point or phase structure transition. So the first example is the diffuse reflectance high temperature chamber from ARIC that allows to do reaction or analysis of material from room temperature to 600 degrees Celsius. And it was said or pointed out in the literature that there is a drift of temperature between the temperature recorded at the sample bed thermocouple and the actual temperature on the sample. So this temperature drift can be up to 100 degrees Celsius at 460 degrees Celsius set point. So this analysis is just made by the temperature you set on your controller versus the temperature recorded with a pyrometer. They did also a reaction study. So if you're studying a catalytic reaction, the rate of reaction should be the same at similar temperature. And this is the example of CO methanation over 16% nickel on alumina catalyst. And we can see, depending on the accessory you're using, the rates are different. So coming from this conclusion, we wanted to look at the calibration of this accessory and how we can approach it. So the first step was to look with an external thermocouple what is the difference between the temperature we set and the temperature we record. So for that, we modify the cell so we can see that the thermocouple that gives the temperature is inside this metallic block where the heater is, and it's not where the sample is. So we customize the cell in order to put a thermocouple inside the catalytic bed or inside the powder bed, and we could record the temperature from the powder versus the temperature of the set point. So in purple, this is the parity line, so 1-to-1 ratio, so the same temperature set versus the temperature recorded. And we can see on several attempts, so this was tried 5 times, we have different temperature curve. And this is because it's very difficult to have a good contact between the thermocouple and the powder bed, and we might record on the top of the powder, so not the actual temperature of your sample. What we have done at the end was to put the thermocouple inside the cup, touching the sample cup. And this is the maximum temperature you can achieve, because this is the temperature that is in contact to your powder. And we can see that even by doing that, we have a difference of 30 degrees Celsius at 200 Celsius set, and 100 Celsius when we set the temperature to 600 degrees Celsius. So this is a good approximation, but it doesn't tell us what is the temperature at the surface we're analyzing. It just tells us what is the temperature inside the cup. So in order to study that, we decided to use a commonly used standard for the thermogravimetric analysis. So the choice of this standard is because it has a well-known decomposition temperature, it has a fast phase transformation, and the change can be observed using FTIR. So the molecule or the compound we decided to use is calcium oxalate monohydrate that leads to a dehydration at around 171 degrees Celsius, then decomposition to form calcium carbonate at 500 degrees Celsius, and complete decomposition at 740 degrees Celsius. So the 2 first events are of interest for analysis because they span within the range of temperature our cell is capable of doing. So the first step was to analyze those materials using TGA. And we first analyze the pure compound using parameters that we will use later on for the FTIR. So nitrogen, a flow of 20 milliliters per minute, and a ramp of 5 degrees Celsius per minute. We analyzed the pure calcium oxalate monohydrate, and we saw the first event at 148 Celsius and the second event at 488 degrees Celsius. And then we decided to look at the diluted sample because by FTIR we want to use a diluted sample to avoid to saturate the detector. So we looked at 2% calcium oxalate monohydrate, and we can see a shift of the temperature at which it reacts. We also did the study of pure potassium bromide, and nothing happened, meaning that the only thing we're seeing is for the calcium oxalate monohydrate in potassium bromide. So now we know the 2 transition temperature, 111 and 462 degrees centigrade. Then we try to compare under the same condition the TGA-MS, so we could confirm that the first event corresponds to the loss of water by looking at the mass 18. The second event corresponding to the loss of carbon dioxide, which is recorded using the mass 44. We look at, under the same condition, the FTIR of these 2 weight percent calcium oxalate monohydrate in potassium bromide, and we can see the decrease of the hydroxyl band by FTIR and a change of the carbonyl band for the compound. So we decided to do this study, or this calibration, using 3 different approaches. The first one, the most commonly used, is integration of functional groups. So we know that we are losing water and we are losing carbon dioxide. So we can study the hydroxyl group. The decrease of the hydroxyl group should give you the complete dehydration of your sample. And the study of the carbonate stretching group will tell you the decomposition of the carbonyl, or carbon dioxide. So if we follow this integration over the range of temperature we set for the cell, we can see that for the hydroxyl, when we plot the derivative, we have a maximum at 110 degrees Celsius compared to the 111 given by the TGA. And when we look at the asymmetric stretching of the oxalate, we can see a change at 535 degrees centigrade, which was supposed to happen at 462. So we can already see that we have a huge disparity between the temperature we set and the actual temperature of decomposition we are probing by FTIR. One of the issues with this technique is everything needs to be done using a baseline, and the integration is subject to the operator error. So everyone can integrate wherever they want and have a different result. That's why we decided to use a second approach that was discussed by a group in 2009, where they demonstrate the potential of using the absolute baseline variation in the mid-IR to study phase transition of material for potassium bromide pellet. This has to do by the fact that at the transition temperature, we have a change of adsorption and scattering coefficient, leading to a change of the baseline. And so we can only look at the single channel in an area where there is no vibrational band, so 2000 reverse centimeter was used. And if we plot just the value of the baseline over the range of temperature and we plot the derivative, we figure out the 2 transition temperature, one at 125, one at 530. This first transition is sharper than the previous one, giving you a more accurate view of the temperature inside. The last approach we try to do is comparison of MS from the TGA and the MS from the FTIR. And we can see for the first transition, it's in good agreement with the previous approach using the baseline variation. So we find 125 degrees Celsius using the FTIR versus 112 using the MS for the TGA. But when we look at the carbon dioxide, we can see that those 2 temperatures are very close and that the carbon dioxide mass signal is broader. And this is because we are decomposing a bulk sample and not just the surface. And this approach cannot be used to accurately determine the temperature at the sample bed. So if I summarize everything compared to our temperature probe, so the thermocouple in the bed and the parity line, we can see those 2 points that agree pretty well with the line, and the 2 points that are the most accurately representing the drift are the one using the second approach. So this is a good way we could use in order to calibrate the temperature for FTIR accessory. Now I will discuss a second problematic, which is non-ambient XRD. This work was done by Nicole Wonderling. It was done using this HTK 1200N from Anton Parr that can span the temperature from room temperature up to 1200 degrees Celsius. We can see that we put the sample here. We have a radiation heating. the temperature probe that is close to the sample, and the windows around it in order to collect the XRD data. It came from, the requirement to do that came from a comparison of our data with different labs across the US. And initially, this accessory was calibrated using the thermal expansion of Seria. And when we compare for a given sample I will discuss later, our data compared to other labs, we are not in the same curve. So there is a need to use a different method in order to calibrate this accessory. And for that, we can use a standard material that has a well-known transformation temperature, a fast phase transformation. This transformation needs to be reversible, and it should have no reaction with the sample holder. And what was used by Nicole for this study is 6 different material that has sharp melting point or phase change across the different temperature range this accessory can achieve. So the first step for this analysis is to just analyze the pure material using XRD and making sure that the compound we are using is the real compound. So this was done on the sucrose, the quartz, the sodium acetate, and the sodium chloride. So confirming that this is the material we are interested in. And then if we look at the analysis of the decomposition temperature of sucrose over the range of temperature, we can see a complete disappearance, or a start of disappearance of the diffraction pattern at 182 degrees Celsius and complete disappearance at 185 degrees centigrade, which is in good agreement with a melting point in the literature of 186. This was done as well for the sodium acetate, and it could be seen that the decomposition temperature was around 326 degrees centigrade, where we start seeing a new peak, which is very close to the theoretical of 324 degrees centigrade. And so with doing this experiment with all those different standards, we can compare the expected temperature with the mid-range of the actual value we got using our experiment, leading to a calibration curve that can be fitted and used in order to correct for the temperature deviation. In order to validate, which is very important, these results, this is a work that Nicole did with other laboratory. They use a magnesium stabilized aluminum titanate material that has a specific despacing change between the 250 and 002 diffraction pattern. And this change, the study of this change across the temperature can be compared across lab. So we can see in this point, the actual versus set point are pretty accurate. And this is because the accessory was new. But this is a good method in order to verify that your accessory did not drift over time. And nowadays, if we compare the results recorded at Penn State versus other lab, we are perfectly in line with other labs across the US. So this validation is very important in order to have reproducible results, not only within Penn State, but across any type of lab. So I just want to take this opportunity to give a general conclusion. In order to have reproducible and rigorous thermal analysis, we need to make sure that our accessory is calibrated, make sure that the furnace is clean, the sample preparation is the same, temperature range is the same, temperature ramp is the same, and the sample atmosphere is the same. This is one of the reasons why the method section in the literature is extremely important in order to be able to reproduce it, not only just the parameter we are using or the sample preparation, but also the way the instrument has been calibrated in order to have other people replicate your experiment. So for the calibration, we need to use a thermometric standard that covers the entire temperature range. 1 point is not enough. The calibration needs to be done for each condition that are used, so atmosphere, flow rate ramp, and the calibration needs to be redone every time there is a change of thermocouple or the controller is modified, because this affects the temperature you will get. For the validation, this is extremely important. You need to choose a material that gives you a temperature validation over the range, so something that changes over time, which is what the magnesium stabilized aluminum titanate was used for. And if you can, use a cross-validation with different labs at different locations to make sure that you get the same results. So I just use this target representation that is extremely used in analytical science to represent the difference between reproducibility and accuracy. In the first point, we can see that none of the results are reproducible and accurate. In the second, we can see that it's reproducible, but only locally. So it's reproducible if you use the same instrument in the same lab, you can get the same results. But the results cannot be concluded with another lab because it's not accurate. The last point, this is what reproducibility and rigor means, meaning that you are accurate, you can give to another lab, they will have exactly the same results, and it's reproducible, meaning everybody can get the same answer. Thank you very much for your attention, and thank you for watching. I will be answering any question you have.
For the IR experiments, when you're changing temperatures, how do you ensure that temperature drift is stopped? Like, let's say, for example, you collect a data point at 40 degrees Celsius, you change the temperature to 60 degrees Celsius on the controller. How do you know when to collect your 60 degrees Celsius data point?
That's a good question. Thank you for the question. So first of all, this temperature calibration is proper for this particular rate or particular ramp of temperature. And if you change the temperature ramp, then you need to do another calibration to make sure that the temperature is stable. Second of all, I use, and this is the main difference between thermal analysis methods such as TGA and DSE, where the ramp is extremely fast, and spectroscopic or diffraction methods where the acquisition of the data takes time, so the ramp needs to be slower. And that's why I did this comparison with the TGA under the same condition for the FTIR, because I had to reduce the ramp to 5 degrees per minute in order to make sure that I have identical data. And we can see in the theoretical value, so those values are taken from an application note from NETCH. They use a 10 Kelvin per minute, I use 5, and already for the pure sample, I have quite a difference for the first transition and the second transition. So that's why it's very important to cross-reference your calibration with another technique.
Any other questions?
Hey, Jordan. Yeah, thanks for the talk. What about temperature variations across the sample itself? Like, are some of the transitions that you see there broadened because different parts of the sample are actually at different temperatures?
This is correct. This is even better viewed in the MS data. So we have exactly the same shape of the carbon dioxide, except that for the TGA, I use 8 milligrams of sample. For the FTIR, it's more in the order of 30 milligrams. And that's why you have exactly the same signal, but it's broadened. And according to the previous analysis, where the surface, since the FTIR is probing the surface, so you will have the same answer as what you want to answer using this calibration, because this is what you're looking at. And so we have 530 degrees Celsius, where there is still some decomposition of carbon dioxide, but it's very much at the end and not at the optimum of the derivative peak. And this is why doing the spectroscopy at the same time is very important, because that gives you the value where you are analyzing the sample. The same for XRD. If you have a large sample, the edge might warm up quicker. I mean, especially this configuration with this sample cup, the edge will definitely warm up faster than the center where you're probing your experiments.